One of the most useful ways to use components is to add several vectors. So we're going to try to add all three of these vectors, otherwise known as finding the resultant. We could do this using the head to tail method that you've learned before, but this is just another technique in your toolbox. We're going to start by drawing each vector using the same method that we went over in the last video. I'm going to use a 1-to-1 scale, so I'm just going to say 1 meter per second. These are velocity vectors, they tell speed and direction, is equal to 1 centimeter. All right, and I'm going to start by drawing a 5 centimeter line going south. If you want a little coordinate system here, never eat shredded meat. Okay, so straight south, I need a 5 centimeter line, so I'm going to go ahead and do that. All right, and then this is a vector, so make sure that you put an arrowhead on it. Not a bad idea to label it. Okay, and then the thing about this is I don't need to draw them head to tail. I can just kind of draw them all over the place. So I'm going to move this down slightly so that we can get a little bit better view here. Okay, all right. So I'm going to draw my next vector just somewhere on here, an 8 meter per second west. So we'll draw this one, and I'll just kind of draw it this way. Make sure there's room here. There it is. And then finally, I'm going to draw a 6 centimeter vector going towards 60 degrees. So I'm just going to make a dot here where I want to start, and I make a dot at 60 degrees. Okay, and then I'm going to draw a 6 centimeter line up towards that 60 degrees. Now, how do you find the components of something that's going horizontally and vertically? All right, well, remember, a component is how much of this is going left and how much is going up. So if I look at the first vector here, okay, and I'm just going to add signs here. So anything up or right is positive, anything down or left is negative. So if I look at this thing, how much is this going down? It's going down exactly 5. All right, I'm going to do these in centimeters. So I can go ahead and say that the y component of this is 5, but because it's going down, I have to put in a negative. And this isn't going right or left at all, so I can go ahead and put a 0. In fact, it turns out I didn't need to draw a scaled vector diagram to figure that out. If you're right on the coordinate system, you can just figure it out. Similarly, with this 8 centimeter vector, all right, it's going 8 centimeters left, so the x component is -8, negative because it's going left, and 8 because that's how long it is, and it's not going up or down at all, so this is 0. This one we actually have to use the technique we learned before, and I'm going to draw this as a triangle. So very lightly I'm going to sketch these in, seeing how much of this vector goes up and how much of it is directed to the right. All right, I'll get rid of that. Put in my arrows, so since the 6 centimeter vector is going a rightish, this goes, the x component is right. We can call that cx. And since this is going upish, the y component is cy. Okay, and that's going up this way. Okay, and again, if I took these two vectors and added them up, I would get this vector. So component is kind of like going backwards. All right, now you could do trig to figure this out, but we're going to do it this time graphically. So I'm going to go ahead and measure this. This is 3 centimeters. It's about 3.1. Yeah, I'll go 3.1. So, and it's going to the right. So my x component is 3.1, and my y component is about 5.1. If we're doing this mathematically, we might get slightly more accurate answers, but this is still a useful tool. Now, the beauty of components is that all the x components can be added like regular numbers, and similarly for the y. So if I add -8 to 3.1, I'm going to get just shy of 5. Doing this in my head, I'm going to go with 4.9. And it's a -4.9. And then this here is just this is just going to be a 0.1. Okay, now we're not done because what we wanted to do is add these three vectors together. So now what we have to do is then take our resultant, find the resultant of those. So I'm going to move this down. All right, we're going to see our sum there. Okay, and I'm going to go ahead and draw this. So my x component, I'm going to just start somewhere here, is going to be a negative 4.9. So I'm going to draw a 4.9 centimeter line going left. And the sum is also a vector, so I need to make sure I put an arrowhead on that. And then you need to draw the other one. I'm going to do the head to tail method of drawing it because this is nice. So this is going to be super tiny, but there's my super tiny y component. And then the resultant, let's see, is from start to finish. Oop, boy, there it is. Okay. If I measure this, I get it to be just about 5 centimeters. So the magnitude of my resultant is 5 centimeters. I need to convert that back to meters per second. Ooh, you can't see what I'm doing. Sorry about that. All right. So this is me. I drew the x component this way. I drew a tiny y component, and there's my resultant. All right. So the magnitude is 5 centimeters, but since these are velocity vectors, and the original scale was in meters per second, I need to say it's 5 meters per second. And the direction is, we'll have some more instructions on direction later, but it's just shy of, so this is in the second quadrant, so it's nearly 180 degrees. It's just shy of that. I'm going to put in 179 degrees. So when I add the three vectors that were given, all right, I get that the magnitude of the resultant is 5 meters per second at 179 degrees. And you could have found this using the methods we learned last time, but this is just another thing in your toolbox.